and I'm in Chungang University. Yeah. Here's the contents that I talked. Yeah, just to go. Yeah. Shown here is the nice picture. I mean, LED applications. So they believe that LED can replace the fluorescent lamp because of their high efficiency. So maybe you can imagine that the market size if this LED can replace this fluorescent lamp. If you are familiar with this picture, this one is from Luminescent. Whatever, we have a white LED structure. I mean, we can make a lot of white LED structure. Maybe you simply combine red, green, blue LED. In this case, the color rendering is very, very good. Also, very efficient light, efficient. So, I heard that they take this structure for the backlight of large LCD TV. So, it's a good one. But it has a problem. I mean, it's a very, expensive. Also, they have to drive each LED. So, has some difficulty in driving this structure. But phosphor converted white LED is very simple. Maybe, the main market is this, as Dr. and Professor Anderson said this morning. So, they use a blue LED and just to put the real yellow phosphor on that LED. Then you can see a white light, or maybe the main application of this. So maybe you see this one. As you see, this is spectral. We need more light, LED light. So we use this blue and green and red. So if you take a look at this stuff, obviously you see some efficiency in red light. So another choice is this, blue LED and put the green phosphor and red phosphorus. As a green phosphorus, they use thiogallate. Red phosphor, strontium sulfide. It was patented by Luminescent. Another one is UV LED. Then you just put the red, green, blue phosphorus on that UV LED. Then you can see blue, green, red, like a CRT or any other type of display. So maybe. So in this talk, we need to put more attention on that these phosphors. What is the issue and how can we synthesize that phosphorus and what is the groundwork, that kind of stuff. Why tricolor LED? It's simple. If you have a tricolor LED, then you can find a real good color rendering. So application can be wider in this case. Another big issue is patent. It's a very cost-effective structure. Also, maybe you can need only one drive chip for this stuff. Very good, but all this structure is patented by Mitsuya. So it's really hard to penetrate the market. Also, the Korean market has a very difficulty in penetrating the market. So we have maybe 30, near 20 or 30 small companies to enter this market, but they all has that kind of problem. Maybe they can find the real good phosphorus with UV LED, they can maybe penetrate to the market without any problem of this patent. Yeah. So, as I told you, I'm focusing on the phosphorus. So here's the research trend. We have to increase that efficiency. Also, we have to increase that color rendering index. Then maybe if you have a pure RGB color, then you can automatically obtain this good color rendering. this efficiency is also another issue. At this moment, the blue LED blue LED with the YAG phosphor, the color rendering is near 75. Also, efficiency in this level. But for instance, UV LED, the color rendering is also good, but the efficiency is relatively low. So they have some problem to penetrate to the market. So if you increase that chip efficiency and find the real good phosphorus for this, then you can control the hold at the market here. Yeah, I just put the little materials here, the patent materials. So Nietzsche controlled at the market with the YAG phosphors. And the Oslam, also material companies, they develop PEG phosphors. It's simply just to put the terbium ions on the YAG materials. But they can avoid that the patent with the Nietzsche. The emerging company Luminescent has a lot of patent on this stuff. Maybe not this year, maybe sulfide, CO galate, many materials. Also, Jelco is a very, very aggressive companies to develop this kind of stuff. Yeah, here Luminescent. Okay, let's. It's a patent alliance. It's a typical case that the phosphor controlled at the market. See, even though we have a lot of chip companies, I'm talking about the white LED, not this big LED. This material company controlled at the market with these materials, phosphor materials. Nietzsche also has a blue chip patent, but they have a very strong, in white LED with YAG phosphors. Maybe in the morning session, another person talk about the market size, so I just skip it. What I know is the market size of this white LED is same as the whole display market, so it's a big one. So what I want to show you is this stuff. What kind of work we have to do, and what is the approach for this stuff. Phosphor materials. Also, we need a sort of a polymer, encapsulant. In this case, refractive index is very important. The gallium nitride, the refractive index is 2.0 something. So, in order to take the photon out of that gallium nitride, the refractive index has to be similar to that gallium nitride. So we need to increase that the refractive index in this encapsulant. What about big issues these phosphor materials? So what kind of phosphor we need? The most important thing is color. You see, red, green, blue. In case of UV LED, the most efficient chip is near 405 in this region. If you have a UV LED, then you see a kind of a violet color of that chip. So if you put that the red, green, and blue phosphors, then you can get to the white point here. At this moment, okay, take a look at another side. This one is a typical example what kind of phosphor we need. For instance, blue, Nietzsche patent, they use a 465 nanometer chip here. This one is emission from the chip. So for the phosphor, you have, this phosphor has to absorb a lot of photon. In this region. Then also that the phosphor has to emit the color that you want. In this case, orange. Then this blue color plus orange, then can make a white color. See, this one is the spectrum of blue one is the spectrum of YAG phosphor. Very fortunately, YAG is a very famous material. Thank you. See, this blue color is YAG phosphor. YAG is very famous material. I mean, long time ago they used that YAG material, I mean CRT. But very fortunately, near the 465 nanometer, they can absorb a lot of photon in this energy band. Also, they emit the orange color here. Perfectly match with the 465 nanometer LED chip. It's perfect. Whatever they patent this structure, nobody can, I mean, avoid that patent issue. So, for instance, tag is exactly same as YAG. As the activator, they just put a little terbium. That in that case, we have a very, very small energy band here, terbium. Then they insist that tag is a different material from YAG. It's a trick kind of. Whatever. So we need I mean, with this view graph, we may know everything about the phosphor. In this LED applications, the first one, you have to absorb a lot of photon at the range of LED emission, then emit proper color. So, what kind of work we have to do? For instance, this one. The LED chip is also different energy efficiency near maybe 465, 460, 455. Then we have to adjust that phosphor materials to fit that spectrum. How could you do that? Just to, in this case, YAG. Just to put the different element on that crystal. Then the crystal field a little bit changed. Also, in that case, then energy band slightly changed, then maybe emit the long wavelength and the short wavelength. That's a typical adjustment. If you have a proper LED chip, then maybe you can adjust that the phosphor to fit that LED chip. Korean character. Whatever, except the professor and some application. It's a typical case. First, you have to design that phosphor, maybe. Then, how to synthesize that phosphor. Then, identify that the crystal structure. And another issue is this. Even though you have a nice phosphor, if you do not treat that phosphor properly, then you cannot use that phosphor. So, it's very important to adjust that property for processability. Yeah. So, how could you design that phosphor? You know, we have a lot of elements here. So, a lot of cases here. So, which one is the best one? It's a kind of finding that the gold in the sand. Another one is, this one is rare earth, which activate ions. So you can just guess which one is the proper color. Maybe, for instance, europium ion and terbium ion. Then maybe if you have to 4D transition, then maybe the color will be red or orange. We just can guess. And with that ion, maybe you have to select the host lattice. I mean, fit that. Activate, settle down that activate ions on the host lattice. So, we can think about a lot of combinations. But you know, the starting point is this stuff. Maybe the easiest way is benchmarking. So another companies, they develop some stuff, then that will be a starting point. Whatever we have to avoid at the patent issues. Another one is crystal. We have a JSPD card, and for instance, I'll show you later. Maybe we have a lot of sulfide material, oxide material, then they have their own crystal structure. Then maybe you can put that activate ions on that hospital lattice, and it will be working, then maybe we will have a good color. That kind of stuff is another approach. Another one is knowledge. Maybe we have optical data, crystal field data, band data, then based on this knowledge, maybe we can design the force point. Then start to synthesize that force point. In fact, 3 years ago I started this study. So first, I examine all that, in this case, sulfur materials. Sulfur materials, and process parameter is this. Then we have to, first they have their own crystal structure, and in this stuff we put the activate ions here, then what kind of color we have, that kind of stuff. A lot of work has to be done. So it's a kind of trial and error, very, very tedious job. Another sulfur-based phosphors. Yeah. In this case, maybe benchmark. Maybe we can find the absorption band and the emission band, and with what material has to, are patented by some companies. We examine all that stuff and find the candidate. Yeah. Keep going. Yeah. Oxide material, nitride. Yes. This one is a very emerging materials, nitride phosphors. Usually in CRT or PDP, FED, many phosphors are oxide or sulfide bases. But these days, nitride is very important because it absorbs the energy near the visible range, because 460 or even UV 405 nanometer. So, but LED phosphor has to absorb the visible range. The good candidate is nitride material. Yeah. So we identify some materials here: oxide, sulfide, nitride, oxide. Yeah. So from now, I'll show you one typical case of how can we obtain the proper materials. So it's an oxide systems. Very fortunately, I found this work published near 1960, a long time ago, maybe 30 years ago. But I found that the emission range is near here. 560 nanometer. Also, it absorbs near 400 to 450 nanometer. So it's a good candidate. Also, this scholar working on that materials, and many data are available for this material system. So choose activator, European. So 5D4 F emission from UV to yellow. So you can cover, as I told you, from visual range for 500 to 600. So here's the typical. If the crystal field is weak and the amount of covalence, the covalence, amount of covalence low, then the emission shift to high energy, short wavelength. So what if the station and the luminescence of European ion on the host lattice with alkaline earth ions in a low? So I try to replace that alkaline ions, another materials. So we try this material, Mg2SiO. After synthesize that material, first we have to identify that the crystal. Yeah. and maybe another it's different, right? So another, we can imagine that this one system is different from this one. It's a morphology. So we need to, improve this quality. Not good enough for the processability. So maybe if we use flux, then we can increase that particle size, and we can have a more round type of phosphorus. Also, we have to find a smoother surface. Maybe still need to improve this morphology. Yes, maybe it's a. That the system we just replace alkali earth ions. On the cation, and see the wavelengths shift to the higher energies. But very unfortunately, the increase. The efficiency is dramatically decreased in this case. But in Mg ions, very, very interesting stuff. The original orthosilicate is near here. So what I need is this energy band. Have to absorb a lot of energy here. Also emit blue or green or red. In this case, if we replace that strontium ion to Mg ion, then the absorption band move to the short wavelength. Yeah. Also, emission band was shift to the 4 or 5 blue ray range. In this case, very fortunately, the efficiency is increased very much. It's lucky. So maybe I believe that maybe if we do a little more work, morphology or some particle size, then it will be can use for the 4 or 5 nanometer. UV LED. Phosphor for UV LED applications. Of course, we have to find the green and the red. But this, up to now we have a nice blue phosphorus. Also, we have, maybe next time I will show you. We also have a nice green phosphorus for near 4 or 5 range. It's not yet done. Even though you have a nice spectrum, you also have to do something for the real applications. For instance, you have to prevent some water absorption, but you have to keep the longevity of this phosphorus. So need to treat the surface. This is a typical example. Maybe just a micro coating or nano coating. And if you, in this case, if you put a little heat in this case, then you can have a very encapsulation, continuous coating. Next. So take a look at that longevity. Then in this case, it's better. But the case is different in each case. Yeah. See, it's a longevity data. If you put that, if you coat this powder, then obviously increase that longevity. So, for instance, sulfide phosphor has to coat the materials for applications. This is a typical work, for the phosphorus. So, if I just take a summary and try to show you how to design and synthesize the phosphorus. And I taking that the silicate-based phosphorus, I try to show you how to control that the emission spectrum, also excitation spectrum. We have a lot of, physical or chemical background for this. We have to have a lot of physical chemical background to study this phosphorus, for instance, covalency bonding state and some energy transport, that stuff. But the real situation is hard working. Just to try. You can talk a lot about theoretical background for this phosphorus, but point is hard working. In my lab, we find the blue phosphorus and green phosphorus that still need to increase that efficiency more than maybe 30%. The important thing is, in order to be a winner of this market, you have to really number one in the world. There's no chance to second person in this business. Thank you.